All right, so here's the second part of lesson 3-6, just with a couple extra rules related to polynomials. I want to start out by practicing one more example like we did in the first part of our video. The problem says, how many imaginary solutions does this graph shown below actually contain? So the first thing I'm going to do with this problem here is I'm going to look at the bumps of this graph and figure out what's going on there. So if I look at this picture right here, 1, 2, 3, 4, 5, and then there's this weird thing going on right here. So that means my picture, if I see 5 clear bumps, it's at least degree 6, but honestly, this thing is sort of like a bump right there. So we're going to be probably looking at least degree 8, because something strange is going on with this part of the picture. If it was just degree 6, we would see a down arrow right here, and that would be it. So really, we're looking at a picture that's at least degree 8. If I look at my answers that I can actually see, I see an answer right here where it hits the x-axis, and this one slices through like normal. So this answer right here only appears to occur one time. And then I go over here to this guy. This one does a weird kind of swervy deal. At this point, it's an inflection points. So that would tell me this answer repeats at least 3 times. It's got to be an odd number of repeats. If it was like a 4 repeat situation, it would do something where it would come back and go the same way. So this repeats an odd amount of times. That means I have 4 solutions that are accounted for right now. But on an 8th power graph, that would mean at least 4 of these solutions must be imaginary. So there's not like a super clean, easy rule for these problems. It's more just a thinking process right here and figuring out, based on what you see, how many answers have to be imaginary. The purpose of this video isn't to get you guys to be like a super expert, oh, I know the exact answers. It's just meant to get you to think about what the answers are and what else is going on. So I want to show you guys a couple theorems that are related to answers to polynomial graphs. So these two theorems kind of go together, and you'll see why as I talk about them here, but they're called the conjugate root theorems, and they work for complex, so imaginary roots, and also for irrational roots. Think about last chapter. When we would solve quadratic equations, our answers would always end up looking like 3 plus or minus 5i, or like -2 plus or minus 3 root 7, stuff like this. Anytime you have answers that are sort of ugly looking, with i's or with square roots, they actually come in pairs where you have plus or minus the same thing, plus or minus the same thing. That's what these theorems say. I look at the conjugate root theorems as buy one, get one free. Or BOGO, so it's like a little BOGO sale going on for our complex and irrational roots. So what the theorems actually say here is that if a plus bi is a solution to a polynomial, so is a minus bi. And then the irrational root theorem is going to say the same thing, but a plus square root of b means a minus square root of b is a solution as well. So if you know one of these things is a solution, the other is going to be as well, because they come in pairs. This rule does not apply to normal, like rational, clean solutions. Because picture if you were solving a quadratic and you got down to like 3 plus or minus 4, you're going to have 3 plus 4 is 7, and 3 minus 4 is something entirely different, -1. These do not come in pairs like this does or like this does as well. So let me show you how this is actually helpful here using this example. It says that a polynomial has the following solutions. So what is the minimum degree possible for this polynomial? According to this rule, when you have square root ugly solutions and I solutions, the conjugate is also going to be a solution even if they don't tell you. So if square root 5 is a solution, negative square root of 5 is also a solution even if they didn't specify that in the problem. If 4 minus 2i is a solution, well, 4 plus 2i must also be an answer, even if they didn't tell us. That's what these theorems right here say. They come in pairs. On the other hand, we've got this guy over here, 3/4. 3/4 is not imaginary. It is not irrational. So this does not apply to the theorem right here. That's like this situation in green. We just have 3/4 and that's it. So I count up 1, 2, 3, 4, 5 solutions, meaning that this problem must be at least degree 5. It could be higher if any of these answers repeat themselves, but this is the minimum degree possible. Then they ask us to give the equation. I'm going to do this in factored form. I'm not going to make you guys FOIL this all out because it's kind of unpleasant. But if I were to write out the equation like it says to do right here, I'm going to have y equals. And what I'm going to do is make a parenthesis out of each of these answers. So if I want my answer to be the square root of 5, my parenthesis is going to say just x minus square root 5. If I want negative square root of 5 to be an answer, I'm going to have x plus the square root of 5, and I'm going to keep going the same way. Now, when you have a binomial or more than one term going on, you have to be a little bit careful on how you write your parenthesis. So if I want 4 minus 2i to be a solution, I'm going to act like I plugged in a 4 minus 2i for x to this parenthesis. You want this to cancel out, so you end up getting a 0 for your parenthesis. So what I'm going to do right here, if I have a positive 4, I need to have a negative 4 in my parentheses to cancel it out right there. And if I have a negative 2i, I need a positive 2i to also cancel it out. So this parenthesis, when you plug in a 4 minus 2i, will get you out as 0. Thinking about the same thing with my next parenthesis, if I want 4 plus 2i to be an answer, I need to cancel out a positive 4, so I'm going to do negative 4. And I need to cancel out a positive 2i, so I'm going to do negative 2i. My last parenthesis is 3/4, so I'm going to have x minus 3/4. You also can get fancier with this guy right here. Instead of doing x minus 3/4, what I can do is think about what that parenthesis would have said to solve it right here to get 3/4. And that actually is going to be a 4x minus 3. Because if you add 3 and divide by 4, you get 3/4. So it's up to you if you write it this way or this way, but that would be your parenthesis. Now, we could do standard form and FOIL all of this out, but that's just going to be horrible, so I'm not going to bother doing that in this video. This would just be how you leave your equation. I have one last little quick thing I want to do with you guys right here, and this is unrelated to what I was just teaching you, but it leads into next lesson. Let's say I asked you to divide two polynomials, because that's where this is going to be headed in the next lesson, is how you do division with polynomials, and I gave you a problem like this. What you're going to actually do is factor the top, or factor whatever you can in a problem like this. If you do magic numbers on this top part, it turns into x plus 2 and x plus 5. So what you frequently try to do when you're dividing with polynomials is see if they factor. And the way that this worked out, these parentheses are the same. So you actually can cancel them out and you just get x plus 5 for your solution. I'm kind of rushing through this and we'll do more with it starting in the next lesson. But if you factor something and it cancels, that's a great way to do division with polynomials.